Hi everyone. So in this video we introduce batch normalization, which is basically a strategy that is often crucial to the success or for enabling learning, especially in deeper networks that are very deep to enable having further layers, and in recurrent networks. So basically, we first define what's the problem that batch normalization is alleviating, and then discuss why is this problem evident or more pronounced in deeper networks and recurrent networks, and then we discuss how, like, what's the strategy, right? So the problem is basically that in each update, while training neural networks, in each update, we change the values of parameters, of so many parameters in so many layers, right? Simultaneously at the same time. That happens in deeper networks, right? In recurrent networks, that happens automatically because of the recurrence relationship. And we will shed more light on that in the next section when discussing recurrent networks. But the idea is that you can think of a recurrent network as that there is a feedback loop from the layer to itself, right? So the same parameter gets raised to a high power, right? So if I update that parameter, it's as if I am updating multiple parameters. If I unfold the feedback loops, if I unfold what's called the unfolded computational graph of the recurrent network, right? So in general, this simultaneous update of parameters can lead to unexpected results, right? So the problem is the following. I have, let's say, a 10-layer network, right? And then I do the forward propagation, I compute the loss, and then I compute the gradient of the loss with respect to each parameters, right? Now, this gradient is computed assuming that the other parameters are fixed, right? So for example, if I have a single output, let's call it y, right? And y equal w1 times w2 times w3 times w4 and so on up to w10, right? w1 up to w10 are weight parameters in different layers. So think of this as a line, a network that's a line. w1 is the parameter in the first layer, w2 in the second layer, w3 in the third layer, and so on, right? When I compute the derivative of y with respect to w2, I get w1, w3, w4 up to w10. And this is equal to the current values of w1 times w3 times w4 up to w10, right? If I compute the derivative of y with respect to w10, I get a multiplication of w2 up to w10. And this multiplication is evaluated using their current values, right? Now, after I update the parameters, I am updating all 10 values, right? So that could lead to unexpected results because this update was computed based on a gradient that assumed the current values for the parameters. If there is a multiplication of many of these parameters and I'm updating all of them, then actually that update can lead to results that the gradient didn't take into account. Right? That's one problem. Another problem, that higher order effects, right, not taken into account while computing the first order, if you're doing gradient descent, like stochastic gradient descent, or even second order method, like Newton's method or conjugate gradients, or any of the methods that rely on computation or approximate computation of the Hessian. These methods would not take into account higher order derivatives. These higher order effects can be significant and depend on the multiplication of many weight parameters as well, not just the first order, right? So even the first order or the second order derivative has effects that are not taken into account because I do the simultaneous update of the parameters, while in computing the derivative itself, I am assuming that the parameters are fixed to their current values. Another impact is the higher order effects beyond the second order or beyond the first order, depending on the algorithm you are using, on the optimization strategy. That can depend on this simultaneous update and can be significant, right? So this is the first part. This is the description of the problem, the simultaneous update of parameters, right, can lead to unexpected results. Another way of thinking of that is that the statistics that each layer sees can change significantly, right? So, for example, the second layer is trained based on the inputs to the second layer are outputs of the first layer, right? So the second layer, the whole training process of the second layer is assuming some kind of statistics for its input, which is output from the first layer. These statistics, especially in later layers that depend on multiplication of many layers before them, these statistics can change significantly, right? So from one iteration to the next, the statistics of the output of the 9th layer can change significantly. And hence, whatever the 10th layer was trained on will change, right? So the 10th layer was trained using some statistics of its inputs, which are outputs from the 9th layer. These statistics, if they change dramatically, then basically whatever the 10th layer is trained on can be rendered useless in an abrupt way, in a sudden way, right? So this is the phenomena. Now it's clear why it's more pronounced in deeper layers, because the deeper the layers are, the more this impact is, right? And it's also clear why it's in recurrent networks, because in recurrent networks you multiply the same weight by itself multiple times, right? So one update can be thought of as multiple updates in the unfolded computational graph. Right? So if I am multiplying the same parameter by itself 10 times, I unfold that in time into 10 identical parameters. It's as if I am updating all 10 simultaneously at the same time. It can be even more of a problem in recurrent networks, because this update is not random, right? So it happens in the same direction, right? Because they are all corresponding to the same parameter. While in a deeper network, these updates can offset each other, right? So maybe the statistics of the first layer got multiplied by 2, but the statistics in the second layer got multiplied by half. So they could cancel each other, right? So that's why it's more of a problem in recurrent networks, more even than deeper networks. Okay, so what's the solution? The solution is basically to do this many batch normalization, right? So in every training iteration, after you do the update for every layer, you renormalize. You normalize the values of the units, right, by subtracting the mean and dividing by variance, so that the output statistics of each layer is fixed. So the output statistics of each layer after every iteration is basically zero mean and unit variance, right? And that's what happens when you divide by the standard deviation and you subtract the mean, right? So let's think of H as a matrix that represent the activations for a layer across all examples in the mini batch. Right? So the column corresponds to different activations for the same example, and the rows correspond to so one column corresponds to the activations for one unit across different examples, and one row corresponds to the activations for one example across all the units. Okay, so one row, all the units, I span all the units and just one example. One column is one unit. Okay, so take the mean. Let's say mu j is the mean of a column, right? So is the mean value across all examples in the mini batch. That's why it's called batch normalization. So across all examples in the batch or the mini batch, you normalize the statistics of this unit, the first and second order statistics. So you subtract the mean so that you get mean 0, and you divide by the standard deviation. And when you compute the standard deviation, we add, this is just an implementation detail, you add a small positive value to avoid basically dividing by 0, because we divide by the standard deviation. So here the mean is the empirical mean, so m is the number of examples in the mini batch, right? And after you compute the mean, you use it to compute the empirical standard deviation, which is basically the square difference from the mean summed over all the examples and then divided by the number of examples, and then you take the square root of everything. Now at test time, so at training time, you do that for every mini batch, right? After every training iteration. At test time, you use basically the running averages that are computed using the training data, right? Because at test time, you cannot assume that you have access to a group of examples. You might, right? So you cannot rely on test batches to do that, because you want to you want to be able to classify every example by itself without even having other examples. So the values of the mean and standard deviation that are used to normalize the statistics, these values are computed from the training data. Sounds good? So in the next video, we will discuss in more detail. So this is not the end of the story for batch normalization. We will discuss what's the advantage of this basic implementation of batch normalization, and what's the challenges with it, and how to overcome these challenges. Thank you.